Let's talk about one of the biggest paradoxes in all of biology, the brain. The very organ that interprets every sensation you've ever felt, from warmth to a stubbed toe, is completely incapable of feeling pain itself. So what on earth is a headache then? Well, let's dive into the fascinating neuroanatomy to find out.
Okay, so here's our game plan. We're going to start with that central paradox, the painless brain. Then we'll map out exactly which structures can feel pain. We'll get into the nitty-gritty of the nerve fibers that transmit those signals, figure out what actually activates them, and then, most importantly, see how this all plays out in the clinic.
So this is the big question, right? It feels completely counterintuitive. Your brain is mission control for every single feeling, every sensation. It tells you when something is hot, cold, sharp. So how can it be totally numb to its own pain?
All right, first things first. To solve this paradox, we have to start with a really precise neuroanatomical definition of what a headache actually is.
And here is the absolute key takeaway. A headache is not brain pain. It just isn't. The pain is coming from the structure surrounding the brain. Think of it like this. The pain sensors are in the walls, the pipes, and the foundation of the house, but not in the rooms themselves. And those signals are primarily sent through the massive trigeminal nerve and some nerves coming from the very top of your neck.
So here's the direct biological answer to our question. The brain tissue itself, what we call the parenchyma and the cortex, the stuff that does all the thinking, it simply doesn't have any nociceptors. Nociceptors are the specialized nerve endings designed to detect pain. No receptors, no signal. It's as simple as that. The brain is physically unequipped to feel pain.
Okay, so if the brain itself is off the hook, then what parts of your head are actually sending those excruciating pain signals? Let's get out our map and pinpoint the true culprits.
Now, take a look at this list. This is where the action is. You've got the dura mater, that tough, leathery coating that protects the brain. You've got the big blood vessels, like the venous sinuses that drain blood, and major arteries like the middle meningeal artery and those in the circle of Willis that feed it. Then you have some heavy-hitting cranial nerves, the trigeminal, glossopharyngeal, and vagus nerves, plus the top 3 cervical nerve roots, and of course, the scalp on the outside. All of these structures are wired for pain.
And just to hammer the point home, look at the contrast. We already know the brain parenchyma is insensitive, but so are the ependyma, which are the cells lining the fluid-filled ventricles, and the choroid plexus, the little structures that actually make that cerebrospinal fluid. All the core, functional parts of the brain are completely in the dark when it comes to pain.
So we know which structures are yelling, but how do they actually send the message? This is where we need to understand the language of pain, and it's spoken by 2 very different types of nerve fibers.
Think of this as 2 different information networks. The A-delta fibers are the express lane. They're myelinated, meaning they have this fatty insulation that lets the signal just leap down the nerve at incredible speeds. They deliver that ouch signal, a sharp, sudden, easy-to-pinpoint pain. Then you have the C fibers. They're the slow, scenic route. They're unmyelinated, so the signal travels much more slowly. They're responsible for that miserable, dull, throbbing, hard-to-locate ache that can make a headache so debilitating.
Right? We know the structures. We know the nerve fibers carrying the message. But what flips the on switch? What are the actual physical events that trigger these nociceptors to fire in the first place?
It really all boils down to 3 main triggers. First, you have mechanical stretch. Literally, something pulling or putting tension on those sensitive structures like the dura or blood vessels. Second, you have inflammation, a nasty chemical soup of inflammatory molecules that directly irritate the nerve endings. And third, there's vasodilation. When blood vessels widen, they can push against and stretch those same sensitive structures, often in rhythm with your heartbeat, which gives you that classic, horrible throbbing sensation.
So, why does all this matter? I mean, this is more than just a cool biology fact. This foundational knowledge is absolutely critical for diagnosing what's going on with a patient. Let's look at some real-world conditions.
This is a perfect and, frankly, terrifying example. A tumor can grow deep inside the painless brain tissue, and the person might have no idea. It's completely silent. The headache, which is often the first symptom, only starts when that tumor gets big enough to start pushing on and stretching the pain-sensitive meninges surrounding it.
Same principle applies to dangerously high pressure inside the skull. The pressure itself doesn't hurt the brain cells. The headache comes from the fact that the whole system is under strain. It creates this constant, painful tension on the dura and the big blood vessels, which are being stretched from the inside out.
And then there's meningitis.
That trademark severe headache isn't from the infection of the brain tissue itself, it's caused by a massive inflammatory response in those protective layers, the meninges. That chemical soup we talked about is bathing all those pain-sensitive nerve endings, leading to constant, intense, and widespread pain.
So, let's leave you with this to think about. We've established that the pain from meningitis comes from irritating pain pathways like the trigeminal nerve, but why does it so often cause photophobia, an extreme sensitivity to light? It's a fantastic clinical question that forces you to think about how these very distinct pain pathways are interconnected with other major sensory systems in the brain. It's all connected.